So name one substance that is a covalent molecular and one that is covalent network. So you could have picked any of these for covalent molecular: CO2, O2, N2, Cl2, CO, NO2, N2O4, the list goes on and on and on. For covalent network structures are a little bit harder. So you could pick diamond or graphite, both of them are carbon compounds. SiO2, even silicon, just Si, germanium. A lot of the semi-metals will be covalent network structures as well. Any of those you could have picked and you would have been right. Explain why covalent network substances have extremely high boiling points, whereas covalent molecular bonds have low boiling points. Why, if they're bonded with covalent molecular or covalent network, they have such differing boiling points, even though they're all covalently bonded. So covalent molecular substances exist as discrete molecules. They're little groups of atoms together that don't want to talk to each other, to other groups. Each of these molecules is free to move since it's weakly bonded to other molecules in the system. So they might interact a little bit, but they're very weakly interacting. They're not holding each other together. Therefore, in order to boil the molecular substance, very little energy is required to get the particles moving freely. Just a little bit of energy will allow them to, whiz off in their own directions. Now, covalent network substances have lots of atoms bonded to one another in a big network. In order to allow the individual particles the same level of freedom as a gas, so in order to get each of those particles freely moving like a gas, every single bond needs to be broken. Each of that millions and millions of bonds in your crystal need to be broken up. This requires a great amount of energy, contributing to the high boiling point of these substances. So you can see that breaking a million strong bonds is obviously harder than breaking a million weak bonds. So that's why it takes so much more energy. Just because now, instead of the bonds being contained within each molecule, they're actually spread out and branch out into the whole network, making the network stronger than each of these molecules. Explain why covalent network substances often exist as gases. Well, since these substances exist as discrete molecules, there are weak forces holding these individual molecules together. So the molecules will be held together very, very weakly. This means the particles are free to move when excited by thermal energy. So as soon as there's that little bit of energy, they're going to snap off and fly off in whatever direction they want. The reduced intermolecular forces in these substances are the reason why many covalent molecular substances are gases, because there's such little force holding them together that they can be a gas, or they can have the same freedom as a gas when only a little bit of energy goes into them. And that's why a lot of them exist as gases, because of those very weak forces between the molecules. And why are covalent substances not electrically conductive? And I'm talking about covalent substances as a whole, with the exception of graphite, not just covalent molecular or covalent network. Well, electric current obviously requires the movement of free charge. It needs electrons moving, or it needs ions moving, or if you're a physics student, it needs positrons moving. Not that we get lots of positrons anyway, but it needs a charge that's moving in order to get electrical current. Now, in a covalent substance, the valence electrons, so all of the electrons basically, are locked into bonds between atoms and thus are not free to move. So all of the electrons in covalent substances are actually locked in place and they're not allowed to move from place to place. Now, additionally, there are no free charges in the form of ions, which will allow the flow of electricity. So because there's now no ions either, we have no movement of charge, and no movement of charge means no electricity. So that's why covalent substances don't conduct very well, if at all. So question 5. Covalent network substances are often excellent conductors of heat. Explain why this is possible. So in the last question, we just saw that they're all covalent substances are all poor conductors of electricity. But it seems that covalent network substances are excellent conductors of heat. Usually those two things go hand in hand. Why would this be possible? Since the atoms in the lattice are tightly bonded, vibrations from one atom can easily be transferred to adjacent atoms, either through the bond, so the actual vibration of the bond, or if the vibrations are big enough, the nuclei can actually collide with one another. That quick transmission of vibration helps the heat to move across. So this rapid transfer of vibration equates to a high thermal conductivity. So things that allow the vibrations to transmit very quickly have high thermal conductivity, as opposed to things that cannot let those vibrations move from place to place, thus having a low thermal conductivity. So that concludes today's lesson on covalent substances. We looked at the two types of covalent substances, covalent network and covalent molecular, and we've looked at the difference between the two and what makes each of them useful, or at least different from one another in the way that we use them in industry. So in the future, we'll be comparing all the different types of bonding that we've looked at and hopefully we'll see some differences between the three. Look forward to seeing you at our next lesson.